Hello everyone and welcome back to Math 143, Finite Mathematics. In our previous lecture, we learned how to formulate linear programming problems by identifying decision variable, writing objective functions and expressing the constraints. Today, we will learn how to solve these problems graphically. We will see that instead of checking every point in the feasible region, we only need to evaluate the corner points, which makes solving these problems much more efficient. So by the end of today's lecture, you should be able to graph a linear programming problem, identify the feasible region, find all corner points, evaluate the objective functions at each corner, and determine the maximum or minimum value, recognize the situation with multiple optimal solutions or no feasible solution. Okay, let's start. So, the graphical method, every graphical linear programming problem follows exactly the same 6 steps. Right? The first one, graph each constraint as a line. Graph each constraint as a line. Second step, shade the region satisfying each inequality. Second step, shade the region that satisfied each inequality. Third step, identify the feasible region. Step number 3, identify the feasible region. Step number 4, find every corner point. Find all vertices, right? So step number 5, evaluate the objective function at every corner. And step number 6, choose the largest or smallest value depending on the problem, maximization or minimization. So, if you remember these 6 steps, you can solve almost every graphical linear programming problem in this chapter, because we discussed those steps in the previous section also, right? Okay. First, why do we only check corner points? The feasible region contains infinitely many points. Do we really have to test everyone? No. So, we wanted to introduce the corner point theorem. So, one of the most important results in linear programming says that if an optimal solution exists, it always occurs at one of the vertices or corner points of the feasible region. We discussed that theorem within the previous sections, right? So theorem number 1, it says the solution of linear programming problems. If a linear programming problem has a solution, then it must occur at vertex, corner point of the feasible region. Therefore, we don't need to check the infinitely many points. So we just wanted to introduce the corner points, and we just wanted to find out the corner points and draw the polygon, circle every corner, and never test random interior points. We only evaluate the vertices, right? We identify the polygon and just evaluate the corner points, right? Okay. Then let's see the example. Find the maximum and minimum of the objective function given here, x plus 4y equals c. So the feasible region, you can identify the 4 vertices, 4 corner points, and evaluate the objective function z equals x plus 4y at each corner point. So 0, 6, 4, 10, 12, 8, and 15, 0. So C equals 0 plus 4 times 6, 24. Z equals 4 plus 4 times 10, 44. C equals 12 plus 4 times 8, 44. And C equals 15 plus 4 times 0, 15. Okay, what about the maximum? According to the values, the maximum value here 44. So the maximum value is 44. We can identify the 2 points. So we already have the feasible region and we can't make any changes. Our job is much easier in this example. So what happened? What is the maximum? 44. So we can notice something interesting. 2 adjacent vertices give the same value, right? 2 adjacent corner points give the same value. So this means every point on the line segment joining these 2 corner points, joining these 2 vertices is also optimal solution. Every point on the line segment 4, 10 and 12, 8. So that means this line segment, right? So important. So every point on the line segment join in these 2 vertices is also optimal. So therefore there are infinitely many optimal solutions. So this is one of the special case you will see in linear programming. Okay, then let's move forward. So here you can see the example. But before that, I wanted to introduce you the 3 possible outcomes for the linear programming problems when graphing. The 3 possible outcomes. First one, let's say case 1, a unique optimal solution. We saw it in our previous examples, previous sections. One corner gives the highest value. Case 2, multiple optimal solutions. So that is 2 adjacent corners produce the same objective values. So every point between them is also optimal. So case 3, no feasible region so no feasible solution. Actually, we can say no feasible solution. The shaded region never overlap. There is no solution. Right? Also, we discussed bounded and unbounded regions in the previous sections. What happens if the feasible region extended forever? So what happened? So we discussed the unbounded extended infinitely, and bounded feasible region is completely enclosed. Quick review. Recall, a bounded region is completely enclosed. An unbounded region extends infinitely. So the important results, if the feasible region is bounded, both maximum and minimum exist. Bounded, both a maximum and minimum exist. If the feasible region is unbounded, an optimal solution may or may not exist depending on the objective function. Okay, so let's see the quick example. So first quadrant, x greater than 0, y greater than 0. Is this bounded? No, right? Because x greater than 0 and y greater than 0, the feasible region, the first quadrant, unbounded. Second, let's say the feasible region is this. Then what happened? Is this bounded? Yes. Okay, then let's start the example. Here we have maximization problem with the objective function p equals x plus 3y. Subject to the constraints 2x plus y less than or equal 6, x plus y less than or equal 4, x less than or equal 1, x greater than 0, x greater than or equal 0, and y greater than or equal 0. So no rush, work through the 6 steps. Okay, first we have the first constraint 2x plus y equals 6, the boundary line. Second, we have x plus y equals 4. Third, x equals 1, also x equals 0, y equals 0. Let's draw all the constraints. 2x plus y equals 6. Then when x equals 0, y equals 6. When y equals 0, 2x equals 6, that is x equals 3. So the points are 0, 6 and 3, 0. The second one, x plus y equals 4. So when x equals 0, y equals 4. When y equals 0, x equals 4. So the point 0, 4 and 4, 0. And the third one, we have x equals 1, x equals 0, y equals 0. Let's draw the all constraints. X, y, 0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Negative 1, negative 2, negative 1, negative 2. Okay, first one, 2x plus y equals 0 passes through the 0, 6 and 3, 0. Solid line here, right? The solution region below the line. Okay, next one, 0, 4 and 4, 0. Right, again below the line. Okay, then next, x equals 1, that is x equals 1 line. So x equals 1, and also x equals 0, that means y-axis. This is x equals 1, this is x equals 0, and this is y equals 0, x-axis. So then what about the solution region? The solution region would be where? Because x less than 1 for the previous one, x less than 1, the solution region would be that way. And for the first quadrant values, we wanted to get the solution region here, right? Yes, the feasible region, that shaded region. Then let's find the corner points. So what about the corner points? The corner points should be this, 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 and this. Those are the corner points. So the corner points are, so this is 0, 4. This is 0, 0. This is 1, 0. We wanted to find this out. So that is the intersection of x equals 1 and that black line x plus y equals 4. So x equals 1, then y equals 3. So the intersection point 1, 3. There are 4 corner points. And evaluate the objective function. The objective function p equals x plus 3y, corner points 0, 0, 1, 0, 1, 3 and 0, 4. So p equals 0, p equals 1 plus 0, 1, p equals 1 plus 3 times 3, 1 plus 9, 10, p equals 0 plus 3 times 4, 12. So the maximization problem, the maximum value here is 12. The maximum of the objective function p is 12 at corner point 0, 4. So maximum p equals 12 at 0, 4. Okay, so let's go through the minimization problem quickly. Again, minimize the function x plus 2y subject to the constraints given 3x plus 2y, then inequality 12, x plus 2y equals 6 and x equals 0, y equals 1. So quickly go through the constraints. 12, then when x equals 0, 2y equals 12, y equals 6. When y equals 0, 3x equals 12, x equals 4. So the points are 0, 6 and 4, 0 for the first one. For the second one, x plus 2y equals 6. When x equals 0, y equals 3. When y equals 0, x equals 6. So the points are 0, 3 and 6, 0. Also, we have x equals 0 and y equals 1. Then let's quickly draw the graph. All the constraints must have to drawn, right? Okay, let's go. X, y, 0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Negative 1, negative 2, negative 1, negative 2. The first one, 0, 6 and 4, 0. The solid line again. This line is 3x plus 2y equals 12. And the region would be above the line because it says 3x plus 2y greater than 12. The region above the line. Next, 0, 3 and 6, 0. Again, a solid line here, that is x plus 2y equals 6. Again, above the line because it says the region greater than here, right? Above the line here. Okay, next, x equals 0, that means the y-axis. Y-axis. And x greater than 0, x greater than 0, that way. Right? And y equals 1, So we should draw the y equals 1. Let's use this. So y equals 1, that is this. And y greater than 1 means above the y equals 1 line. So then what about the feasible region? The feasible region is the all overlapping. So unbounded region with the corner points this, only 3 corner points, So what are the corner points then? Oh, yes. Yes, only 3 corner points. Let's find the corner points. Okay, corner points. The first one we know 0, 6. The second one we don't know. We wanted to find the intersection of red and purple line. 3x plus 2y equals 12. And the purple one, x plus 2y equals 6. We can easily find it out, right? And also the third corner point, intersection of the y equals 1 and which one? The y equals 1 and the purple line, x plus 2y equals 6. So let's find it out quickly. So 2x equals 6, x equals 3, then 2y equals 3, y equals 3 over 2. So 3 over 2, and y equals 1, then x equals 4, 1. So there are 3 corner points. Let's see. 0, 6, 3 over 2, and 4, 1. Next step, evaluate the objective function with the observed corner point. Evaluate the objective function. So we have minimization function, c equals x plus 2y, corner points 0, 6, 3 over 2, 4, 1. 0 plus 2 times 6, 12. 3 plus 2 times 3 over 2, 6. 4 plus 2 times 1, 6. So then what happened? The minimum value. So minimum value, again we have the line segment is 6 at the line segment 3 over 2 and 4, 1. Infinitely many solutions again, right? Okay, here are additional practice exercises, right? So please make sure to do it by yourself and identify the feasible region. So quickly go through the exercises. So let's summarize today's lesson. Today we learned the graphical method for solving linear programming problems. We learned how to graph constraints, identify the feasible regions, find the corner points, evaluate the objective function, determine the optimal solution, and recognize special cases such as multiple optimal solutions, unbounded feasible regions, and infeasible problems. Remember the most important idea from today's lecture: if an optimal solution exists, it will always occur at one of the corner points of the feasible region. In our next lecture, we will continue applying linear programming problem techniques or linear programming techniques to more realistic business and economic problems. So thanks for watching. I'll see you in the next class.